Hello Calculus 2 class, this is Mr. Blevins, and we are going to discuss something known as solids of revolution, volumes of revolution. And basically what we have here is we got two functions, f of x and g of x. And in Calculus 1, you learned how to find the area between these two, right? It was the definite integral between a and b under f of x minus the definite integral between a and b under g of x, right? Well, what we're going to do right here at the beginning of this course is we're going to take this area that's underneath that and we are going to rotate it around the, in this picture, x-axis. It could be the y-axis. It doesn't have to be the x or y-axis. It can be any line that we call the axis of revolution. And we're going to rotate it around, or the axis of rotation, and we're going to rotate it around that axis. All right, and this is what happens when we make that rotation. If we keep every single one of those pictures there, so like meaning that stays there, that stays there, that stays there, instead of it going away as it rotates, we get what's called the solid of revolution. And we, as we rotate it, we see this 3D object created. Okay, and if we turn it and look through, there's a little hole in the middle along the x-axis where we subtracted out that area below g of x. Okay, and that's what we call a solid of revolution. Now, if there's only one function, like you'll see at the beginning of these, it goes all the way down and touches the x-axis, and there is no hole in it. Okay, and if you look, if I make it transparent, we can see that inner, the rotation, the volume of that inner function. Again, if there was no f of x, only g of x, that would be our solid of revolution instead of a hole. So these are what we call solids of revolutions, and what we're going to talk about, or this first forum this week, is where do these formulas come from? Okay, so this, if you look at this end shape right here, when we have two functions, one above and one below, and we rotate around, we get a washer, and this is called the washer method. When we only have one function, and this is the function, the square root function, when we only have one function and no function below it, there is no hole under the or in the middle of this, what was the washer before, because there is no lower function, and we'll get what's called a disk. And if you look, there are several disks here making up this. This is the square root function. So if I reduce this amount down, there's the square root function, y equals the square root of x. And this is how many disks, if you want to call it that we are putting underneath this thing. So we're putting one, right above 0, and one right here at, maybe 1 or something. And as we make more and more and more, we get more and more of these disk shapes. All right, and the more we make, the better the approximation of the area to the true volume. Okay, this is the true volume, this is the approximation. All right, and then this last one is what we call the Shelle method. And notice this time, as we rotate around, we're not going around the x-axis, we're going around the y-axis, but we're taking that same shape, that same function shape here, and we're sweeping it around the y-axis. So these segments that we have, they are not rotating around this way, creating disk. They're rotating around the y-axis in this case, and they're creating something called shells as we go through. And these are what we're using to approximate the volume. Okay, if you imagine these things, these vertical bars going around that way, we get what we call the Shelle method. So this blue thing that's going around here, this is the 3D volume that we're trying to find, the 3D figure whose volume we're trying to find. And these bars that are underneath there, it's like a Riemann sum in Calculus 1. If I'm looking at it like this, I would be finding the area underneath this curve, trying to find the area underneath this curve with the rectangles. It's very similar to what you did in Calculus 1, the more rectangles you have, the better the approximation. But again, now we are rotating it around an axis, and as we rotate it around an axis, we're now finding volume. Now, when I click this other button, these are what those pieces look like. Those rectangular things, as they're rotated around, that's what they're going to look like. And the more we get, the more they take on the shape, as you see, of that general solid of rotation. Okay, the more and more rectangles that we rotate around the y-axis, the closer we're going to be to the actual volume. It's very similar to Calculus 1 and finding areas. You know, the more rectangles you have, and the smaller the rectangles in width you have, the better the approximation. Alright, it's just now we are rotating about an axis. Okay, so when we are making the width of these things in the x direction and rotating them around the x-axis, we get discs and washers. When we are extending them, again in this case the x direction, but rotating them around the y-axis, we get shells. Okay, and that's the big difference between the two methods. Now let's discuss, where do these formulas come from? So what I want you to do is look at this. This is part of the disk method. Okay, this is the square root function. This is that one we saw that had the square root function. I've added the x-axis and the y-axis on this thing so we can help us come up with where the formula comes from. And I want you to think about where this or what these components of this volume are going to be. That's what we're trying to find. We're trying to find volumes. So this is the radius of this circle right here. On the top and bottom of this is the same width on the top as it is the bottom. And then this guy right here, this is the height between these two circles. Okay, now geometrically, what shape is this? That's going to give you the volume formula. Okay, we're adding up a bunch of, there's 1, there's 2. When I increase the number of segments on here, there's 2 right now. If I increase the number, again, there would be more of them, and they're all touching on the left hand side, as you can see. So there'd be more, and they would be touching on the left hand side, leaving this gap underneath. But what I want you to come up with, what you have to answer in the form is, what is the volume formula here? The volume of this geometric shape, right, is equal to something times something to some power times something. Alright, and that's one of these. That's this one right here. That's one of them. I just kind of rotated it, turned it on its side so you can see the shape of it. And then the other one would have that same volume formula, and the other one, and the other one. So here's what I want you to come up with when you're doing this. Again, think about this is turned on its side. So here's that radius that I have marked R. There it is. Okay, there's R. Let me erase some of these markings so I don't confuse you. There's R, and here is H. So I want you to come up with what is giving us R, what is determining this radius on this thing. Alright, this is the square root function, y equals square root of x. Okay, so what is giving us R in this formula that will show up somewhere on here? And what is determining H? Alright, and as I increase the number of segments, that's going to affect H. Alright, and I want you to come up with, to basically derive where one of these cylinders, or discs, if you want to call them a disc, where one of these volume formulas are coming from, and then just remember we're adding up however many of these we have, which is this number of segments. So, alright, the formula we use in Calculus 1 is N for the number of segments. So I want you to come up with that. I want you, that's the big thing this week is, can you understand where these formulas are coming from? Alright, for the Shelle method, it's a little bit more complicated to come up with the formula. Okay, so what I've done is I've taken this, and this only went around, this is pi radians, so this is only halfway around. So if you can envision one of these things going all the way around rather than stopping, this is what that thing would look like. So it's going halfway around. If you can envision it going all the way around and completing that circle, we'd get something that looks like this. It's kind of like an air filter that goes over top of some type of a motor. So if you could imagine me taking this thing and cutting it right through the middle, there's a hole right there, right? There's a hole in the middle of this thing, and cutting that thing and then laying it flat. So now I've cut it, I've unrolled it, laid it flat, and the same thing will show up that showed up in the last thing, meaning we have heights and we have a radius. If we look at it, this was the original radius. Let me just do it down here. From here out to some representative value in there, wherever we're making these, this is on the left hand side, so that would be the inner edge in this case. Let me kind of erase it so you can see, but it's just somewhere in this little part where there's actual thickness, this little region right here. It's just some value in there is where our radius is going to. When we're doing the left side, it's going to be this one in this picture, the closest, the inner part of this circle. If we're doing the center, it would go out to, say, right there. And if we were doing the right side, it'd go all the way out to the bigger part, would be the radius. But just understand that it's just somewhere in this gap is where the radius went in. So there's our radius. Okay, and why is the radius so important here? Because it's going to give us something to do with this. If I cut this again and unroll it, what is this big long piece with this circle right here? What does this have to do with this? So that's important. What is this up here when I unroll it? All right, and then this guy right here is this, which is the height of the shell. All right, so this is the height of the shell. You also need to tell me what represents the height in this thing. And if you look back on the last slide, what's representing the height here, the width of this this disc, and what's representing the radius, it's different this time. Okay, what's representing the radius in this case from here to here, and what's representing the height is different than it was with the disk method. All right, so remember, this is disk method. We're now kind of deriving shell method. All right, and then so this volume, the volume of this board, if you want to call it that, is the length times the width times the height. Okay, and so we've got a length and a height. We just need to determine this thing right here, the width, or you can call that the height if you want to. What's determining that? What's giving us this, which is this width right here, the width of the thickness of this shell that we create. All right, so if you multiply those things together, you get one of these shells. You get maybe this shell. All right, and then there's another shell inside of that, and another shell inside of that, and there's this one shell on the outside of that. So once again, we're adding up the volume of all of these little boards to approximate our volume. So that's what I want you to do. I want you to multiply these together. This long thing, which is this shell cut and unfolded, this outer edge here, if we cut it and unfold it, this is what we would get right here. This height, right? This height right here is our H. Alright, and then that little width right there, which is the width of each of these. If we cut them uniformly, if we step uniformly, it's the same for all of these. And there's the one that we're looking at. Alright, so what is that little width when we cut it and unfold it? And if you multiply all this together, you get the volume formula for a shell. You add them all up, you approximate the shells. And so the idea is, if you can derive the volume formula for one and add them all up, then you're doing Riemann sums again like we did in Calculus 1. And the limit, as those rectangular widths go to 0, gives us the exact areas, or sorry, the exact volumes in this case. Okay, so that's what I want you to do this week. I want you to come up, what is the volume formula for the shell method? What is the volume formula for the disk method? Where do these formulas come from?